Good afternoon, everyone. This is Samad here from VBind Education Technologies, Mumbai. VBind brings industry experts live into your classrooms, and today we have a session on IC engine. And for this session, we have got Mr. Yash Pal joining us as a master for today. Yash is an alumni of the prestigious National Institute of Technology. He is currently the design engineer with Prigma Edutech, a company changing the way how India learns technology. Yash currently handles R&D as well as the training department of Prigma. So without any further delay, I invite Yash to take over. Yash, a quick update on the number of colleges joined in. We have got Velamal College, then we have got DJ Sangvi College from Mumbai, KK Lal Institute of Engineering from Nasik. So Yash, over to you.
Thank you very much. Welcome you all and good afternoon. I hope I'm audible to everybody.
Yes, your voice is clearly audible in all the colleges.
Yeah, thank you very much. So today we are going to start with a topic that is very, just a minute, I hope the first slide of the is visible to all.
Yes, it isn't visible as of now. Can you please start the share screen option?
Yeah, sure. Yeah, just a minute.
Oh, yes, it's up.
So it's visible, huh?
Yes.
So guys, we are going to start with the IC engine combustion and performance parameter. So we have chose this very idea and this very topic because this topic is very mysterious to us. Nobody till now in this very word could say more confidently about this very combustion. Means nobody could say that what is happening inside the engine. So that's why I took this very topic to discuss with the students, to the engineering students, because this topic is the core topic of the core subject of being taught in automobile engineering or mechanical engineering. So in this very part, if I talk about the main motivation behind the study, that is, we have to see the difference between these two bikes. Basically, we have two bikes having a comparatively same CC engine. If I talk about the KTM 390 and the Royal Enfield 350cc, I hope that everybody is aware of these two bikes. These are very common bikes, and I hope if I talk about the bikes, some of you might have ride these very bikes. So if I talk about the KTM RC 390 and if I talk about Royal Enfield 350cc, these are having a comparatively same CC engine. That is, in a case of KTM 390, that's a 373, and in a case of Royal Enfield, that's a 346. So if I talk about this, both of the bikes do have the same CC engine. But if apart from this, both of the bikes are giving the different performance, different output. If I talk about the power of KTM 390, it's about 42.9 HP. And if I compare it with the Royal Enfield, that's a 19.8 HP. So if I talk about torque, you can see the comprehensive difference between these two things. So the motivation behind this very case study is we have to see that instead of having a same CC engine, why these two engines are different from each other, how these two engines are performing different from each other. So this is we can say that the main quest of the day, and we will talk about these two engines from engineering point of view. Okay, so if I talk about myself, I am Yash Pal and working with Prigma Automotive Solution as a design integration engineer, and I'm currently working on advanced engine management system, and especially for the gasoline engines or petrol engines basically. And if I talk about the Prigma Automotive Solutions, basically we are providing practical training programs in mechanical and automobile engineering, as well as we do provide educational and technical solutions to the industry as well as to the colleges. Okay, and if I talk about the training program that we do provide to the students, that's the vehicle overhauling, motorbike overhauling, engine investigation, vehicle dynamics, and vehicle engine design and dismantling, automobile skill development program, that ASDP. So if I talk about all the programs are designed to give a hand-on experience to the students, and people do on their own in these very programs to enhance their learning, you can say that the technical learning, so that they could have the actual industrial experience through these all the programs. Okay, and apart from this very thing, we also handle the R&D consultancies for the automotive industry, and we have a prestigious clients like a Tata Autocom and TechForce, and if I talk about KSB, so we have a few of the technical clients also. So these are the, if I talk about the company is basically the R&D consultant, and that's the right thing from where we got the technical information, and we, or we can say the technical research. And we thought that why we cannot provide such kind of information or technical information to the students. So that is the main idea behind the conception of this very company. And in a way to provide the practical learning, we started Prigma Automotive Solutions, and we do provide the training, practical training to the students. So now, further on, I'm continuing on the topic of the day, that is the combustion engine combustion study and the performance parameter, and coming back to the motivation point. So guys, I hope all of you are aware of these two bikes, okay? And the parameters that I wrote on the figure on the board are not alien to you. I guess everybody is aware of these all parameters. So the KTM engine do equipped with a single cylinder having a volume is around 373. Okay, and I hope you are all are aware of 373 means the volume, the cc of the engine. Okay, and if I talk about the power, the KTM is producing 42.9 HP, and the torque, if I talk about, that's 35. So if I compare the parameters with the Royal Enfield 350, these parameters, the output parameters of the engine actually varies. That is, the power only goes up to 19.8 HP, and the torque goes only 828 Newton meter. So this is the difference between these two engines, and you know that both of the bikes are for the different purpose, and both of the bikes performs differently. So we have to find it out technically, what is the technical reason or technical aspect lying behind the conception or design of these two engines. Okay. So guys, this is the technical aspect. Okay, if I compare the power to volume ratio, power to volume ratio of the KTM to the power to volume ratio of the RE, that's Royal Enfield 350. If that the value that comes out for KTM 390, it's very, very high as compared to the RE. This means the efficiency of the KTM RC 390 is much better than the Royal Enfield 350. You can think about that. So if I talk about the torque ratio, torque to the volume ratio, that goes only in a case of the KTM, again, it's more than or very higher than that of the RC, we can say RE, the Royal Enfield 350. So from these two figures, basically, we can conclude that the KTM RC 390 engine is more efficient as compared to 350. But actually, is it true or not? We will find out the reasons and answer in upcoming slides. Okay. So, but from these two figures, one thing is clear: the KTM 390 engine is performing better as compared to 350. Okay. But the question is this: are the Royal Enfield people are fooled? Why they cannot make us their 350 engine similar to the 390 in efficiency? So actually, these are the few questions we have to understand technically. So I'm going further on this very study. Okay. So if I talk about the engine design objective, so if I talk about any of the company who design the engine, who manufacture the engines, basically they have the four objectives in front of them before designing any of the engine. Okay, so the first thing is this: the engine should give maximum useful work. That is a torque, maximum useful work. Okay, second thing is that it should emit lowest possible emission in exhaust. And third thing is maximum fuel economy, so that it could play better in a we can say that in the market. And third and the final thing is a smoother operation. So if I talk about any of the company, basically they try to fill these all four parameters in the engine design. But if I talk about the lower cost engines, if I talk about the Hero Honda engines of Passion, Splendor, these are very cost-effective engines. They may comply with the first three aspects, means maximum useful work or lowest possible emissions, maximum fuel efficiency, but bit rough or we can say bit lesser smoother operations. You can understand that these are the basic four parameters behind design of the engines. If you refine all of these parameters step by step, the cost of the engine will increase. And that is why the engine of Yamaha R15 or Yamaha series engines are different or very cost effective and very, very efficient as compared to any of the engines in the category of the bike. So larger you work upon these 4 parameters, larger the cost of the engines. And if you try to give the few of these very parameters, you can do, and respectively the cost of the engine will be very lesser. So these are the basic 4 parameters behind the design of any of the engines. And this is the basic working of the 4-stroke engine. And I hope you all are aware of. The 4 strokes are basically in the working of the 4-stroke engine. First is the intake stroke, through which the air and fuel mixture is induced inside the engine. And second is the compression stroke, which is compressing up the air and fuel mixture. And the third one is the expansion stroke or the power stroke, in which the useful energy of the engine is extracted out in the form of push to the piston. And the final one is the exhaust, through which we are expelling out all of the waste or residue inside the engine. Okay. And now, through this very engine, I'm going to introduce the basic parameter of any of the engine. And some of you, I can understand some of you may be familiar with, but try to go through these all basic parameters of the engines. Okay. First of all, the cylinder. The piston in which the reciprocates, that is known as a cylinder. And that is the volume of this very cylinder is known as the cc of the engine. I mean to say that how much liquid you can pour into this very volume, that could be termed as the cc of the engine. Okay. Similarly, if I talk, and you can check it out in this very cylinder, the piston is reciprocating between 2 extremities, the top one as well as the bottom one. And these 2 are known as the top dead center and the bottom dead center, that you all are already aware of. Okay. And if it define this very cylinder, this cylinder is basically having the 2 parameters, that is a diameter as well as the length. Okay, so this is the main configuration of the engine. This is the main deciding factor of the cylinder, or we can say main depending parameter of the cylinder. It's a diameter as well as the stroke of the engine. In any of the engine, in a different n number of designs that are present in the market, they may have a different kind of a cylinder in the engine. So basically, there are the 3 different kind of cylinders are available in a market on which the actual practical engines are manufactured. And these 3 cylinders are basically, you can see that over, square, and under. And I hope you recall these all parameters. You might have heard these 3 cylinders somewhere in your study. So the over cylinder is basically having the larger diameter and the smaller stroke length. And if I talk about the square, both D and L ratio is, both of the parameters are equals. And if I talk about the under, so the D is smaller than the L. So these are the 3 configurations which are visible, which are available in any of the engine design. Okay, which is available in any of the engine available in the market. Okay, and if I talk about the basic 2 engines on which we started our study, the KTM 390 and 350 Classic, in order to see the difference between these 2 engines from technical point of view. So if I talk about the KTM 390 having a single cylinder, bore is equals to 89 mm, okay, approximately 90 mm, okay. And if I talk about the power, okay, that's written as a power, that's not a power, that's a stroke basically. So the stroke is basically the 60 mm, and if I compare with the RE350, you can check it out. The cylinder of the KTM 390 will be called as the over, and if I talk about the RE350, the cylinder will be known as the under square. Okay, and this is the basic difference between these 2 engines. How you will feel the dug of 350 and how you will feel the high rev power of high revolutions power of the KTM 390. Okay, so we will try to find it out what it means where this very configuration will play difference in the performance of both of the engines. Okay, so for example, again I have just take both the cylinders from both of the engines. Okay, and for example, we have a spark in both of the cases. Right away, I'm just considering in both of the engines, I'm just going to carry forward a small experiment in front of you. And suppose that in both of the engines, we have a similar amount of fuel that we have injected through the carburetor or through the fuel injector. Okay, so you can say that in both of the engines, we suppose we have a similar kind of a fuel. Okay, and that we are going to burn in both of the engines. And again, imagine that both of the cylinders are having efficient or a similar kind of a blast of the fuel. So what you can conclude is, in both of the cylinder, if the air and fuel mixture burns, it will create a similar kind of a pressure. Am I right or not? Okay, so similar kind of a pressure will be generated in both of the cylinders. Okay, so if both of the cylinders having the same amount of the fuel and are burning with a similar kind of efficiency. Okay, so if the both of the cylinders are having the similar, we can say the same pressure, but you know that the area of this KTM 390 is bigger as compared to the area of the 350. So what you can conclude is the force that will exert on the piston in a KTM 390, that will be the higher as compared to the 350 Royal Enfield. So you can conclude as the velocity of the piston in a case of the first cylinder will be the higher than the velocity of the second. And you can conclude that in the same time, the first piston will sustain a larger distance as compared to the second piston. And you can conclude that in a similar time, at the same time, the piston of the KTM 390 will go for the higher revolutions, but the 350 will go for only very less RPM at the same time. Now you can feel that why your 350 Classic or Royal Enfield cannot go beyond your 6,000 RPM of the engine, and that is a reason behind why your KTM 390 can go up to 10,000 or 9,000 RPM of the engine. So we can conclude that the RPM of the first engine will be the higher than the RPM of the second one. Okay, and we can say that the KTM 390 can go from RPM from 800, means 800 is your minimum RPM or the idling RPM, or 10,000 is a maximum possible RPM in a KTM 390. And in a case of RE350, you can go from 700 to 6,000 only, not more than that. And you know that why you cannot go more than that, because you are stuck with the design of the piston. You have increased the length of we can say that stroke length of the engine, and by design you cannot go beyond the 6,000. That is a technical parameter why this 350 cannot go beyond the 6,000. Okay, so I think till this very point everything is clear to you. And one thing you can understand from here, from the engine, like if I talk about the 350, in a case of the 350, we have a blast. In a case of 390, the KTM 390, in both of the engines, we have a similar kind of a blast. Having the same, we can say that similar kind of a blast, but you can imagine that the gases inside the RC390 remains for a longer time. Can you imagine this very point? So my point is, the gases, the burned gases or burning gases during the expansion stroke or during the power strokes remains for a longer time as in a case of the 350 or Royal Enfield. So that is the reason why the 350 or Royal Enfield will have a larger punch, because the burning gases or burned gases remain over there for a longer duration, which continuously push the piston to the we can say the bottom down center of the engine. So that is why the engine, the bullet will have the enough torque as compared to the KTM. So anybody, if anybody who ride both of the bike can judge the difference very considerably. You can find out the difference over here. For example, you are the three people, you are three friends who are riding the bike. So for example, you are riding a KTM, having three friends on a KTM 390. You will feel that your engine is not providing enough torque to get or set into the motion. But if you do the same thing with the 350 Royal Enfield, you will find very easy. You can even increase the lane by with the fourth friend also. You can increase the one more person at the back seat. So it has a huge torque because it has a longer time period for an air fuel mixture to get burned inside the engine. Means for the longer duration, it stay inside the piston and keep pushing the piston downward. But this thing is missing in a KTM 390 because the size, the stroke of the system, the stroke of the cylinder is very short. And similarly, the exhaust valve is required to be open very easy. We can say that very early as compared to the 350 Royal Enfield. That is why the time duration available for the gas to stay inside the cylinder in case of KTM 390 is very less. So that is why the initial punch in a KTM 390 is missing. And you may find the same kind of a punch or torque at a very high engine RPM when you will go at a 60 km per hour, at a 80 km per hour. But when you are running your KTM 390 in traffic, you will feel very miserable where you are, and you will feel very uncomfortable when you are in a traffic because your big 390 is not giving you enough torque so that you could commute in the traffic very comfortably. Okay, so that is why the Bullet is very, very comfortable for the city rides, for the rides at a lower engine RPM, and this is a cruising bike basically, and you can enjoy the ride at very lower engine RPM having very huge torque. So this is the technical reason why the 350 is we can say that the choice of the cruise lover. Okay, so this is the basic reason. Okay, and I'm in the next few of the figures I'm going to show you the performance parameters of the both of the bikes, so that we could compare which bike is better. So whether it's a 390 or is a 350. One thing I want to let you know that over here, none of these bikes is better than other. Actually, both of the bikes are better. One bike is better for something else. One bike is better for something else. So we will try to figure it out where these points are. Okay. So if I talk about the torque, and I hope that everybody is aware of torque. Torque is basically, okay, that I'm not required to go into the basics of the torque. So the torque, there are two graphs, there are two lines are shown in front of you, okay. So first, can you show the cursor on the line? Please raise your hand if you can see the cursor. Yeah, okay, good. I got the response. I was asking, can you see the cursor on the screen? Okay. So my point is, there are the two graphs are shown to you. That is the blue one is the RE350, the Royal Enfield 350, and this is the torque curve of 390 kpm. And if we can compare these two engines in two reasons, first reason is this reason, okay, or beyond 4000 RPM, and the second reason is this reason, below 4000 RPM. Just again, take the same example. For example, you are three friends and you are required to go somewhere else, and you have first option with the let's say 350. Okay, and when you will put your first gear in your 350 Royal Enfield, you will find there is a considerable amount of torque is available at lower engine RPM. Even if you put the vehicle in an even lower engine RPM, you can find a considerable amount of torque available even at lower engine RPM that will push any tremendous amount of the weight on the vehicle. But if you compare this, the same thing with the KTM 390, this is very miserable, very less torque available at very lower engine RPM. And this point is basically the starting point, or known as the idling point. Okay, when you start the vehicle, when you start the bike, basically your bike starts from this point. Okay, and as and when you give the race, the torque of the engine increases in that way. In case of Royal Enfield, and in this case, in case of 390. Okay, so I'm talking about Royal Enfield. Royal Enfield is having a huge torque as compared to this engine, under 4000 RPM. Okay, so if you are a cruise lover, if you are not looking for a bike which can go at very high speed, if you are looking for the torque, the Royal Enfield is a better as compared to the 390 KTM. But if I talk about in this reason, this engine is miserably low as compared to this engine. Now I'm going to show you why this graph is going like in that way. Okay, so why this graph goes up in that way and why it goes down in that way. I'm going to show you how. And show you, I will be going to discuss. I'm going to discuss with you. When you start the engine, basically, when you start the engine, so there is the piston speed of the engine is very low. The piston is reciprocating at very lower engine RPM, and hence it is taking very less amount of air and fuel mixture from the environment. So again, if the air fuel mixture is very less, then it will give a very small amount of punch on a piston. Obviously, it will create a lesser effort on a piston or lesser torque on the piston. Okay, and similarly, if you think about it, whenever you increase the speed of the engine, your piston speed increases considerably, and it will start sucking in lots of amount of air and fuel mixture. And you can talk about when lots of air and fuel mixture is coming inside larger or bigger blast. So that's why with the engine RPM, the torque increases. With the engine RPM, torque increases of any of the engine. If I talk about this or if I talk about this. But after some time, this goes down. So I'm going to show you why it is so. So the reason behind this is so, after some reason, after some of the RPM, this increases because the engine RPM increases, the speed of the piston increases, and it uses a larger amount of the fuel. Okay, but after some time it falls down considerably. Why it is so? It is so because when you increase the speed of the engine, piston goes up and down at very high speed. The time available for the valves to get open and get closed, it is reduced very considerable amount. Okay, so what happens in that case? If the engine is running at very higher engine RPM, the intake valve will not get enough time to induce, or we can say that to allow large amount of air inside it. So with the higher engine RPM, the amount of air and fuel mixture coming inside the engine reduces considerably. So that is known as the volumetric efficiency of the engine. So volumetric efficiency increases with the engine speed, and again further after some time it decreases considerably with the engine RPM. Okay, that is the reason why the torque of any of the engine increases in a first case and then decreases. Okay, so now if I compare these two things, so this graph means the orange one is upper end, it's getting benefit over the 350 bullet, because this engine can go at very higher engine RPM and can draw large amount of fuel inside it as compared to the bullet one, because bullet cannot go beyond 6,000, but this engine can go beyond 6,000 and can go up to 10,000. Okay, so what I can conclude is from this very graph is the lower end torque, or we can say that the traffic torque, the torque of the engine in a traffic, the RE350 will be the winner one. Okay, but if I talk about the torque at a higher engine RPM, or for the racing vehicle, so this vehicle will be at the top position. Okay, so this is the difference between the torque of these 2 points. And now I hope that you understood the torque of the engine and how it changes with the engine RPM and which engine is better in a case of torque. So I conclude from this very point. Okay, so if I move to the next part, power. You can check it out. Although in initial slides I shown that the KTM 390 is having the larger power, means that is a 42.8 HP over here. By mistake over here, like this graph is a little bit slowed down. Okay, so in the initial slide I shown that the KTM 390 is having a 42.8 HP, and this engine is having 19.8 HP only. But point is this required to be understand that this higher the power 42.8 HP is at very higher engine RPM for this engine. Okay, and you can talk about, if I talk about the bullet engine, the Royal Enfield engine, this engine having the 19.8 HP at this very engine RPM. Try to understand what is my point. If you compare both of the bikes at this very RPM, you will find that this again bullet is better than that of the KTM, not the KTM. The KTM is taking benefit only and only of its engine design. Means it can go up to the higher engine RPMs rather than we can say that as compared to the Royal Enfield. If I limit the RPM of the KTM 390 to the 6,000 only, by any mean, by ECU mapping or like ECU design or by anything, if I limit the RPM of the KTM 390 up to 6,000 only, the bullet will be the better design than the KTM. Now you can understand what I am trying to say. So I can conclude from this very point is the KTM is better than bullet in some another aspect. In an aspect, if you are looking for the racing vehicle, and bullet is better than KTM 390 if you are looking for cruising engine, if you're looking for the low engine RPM power. Okay, so this is the difference between these two engines. Now I am going to go into the further little bit advanced factors that you have already or maybe reading or studying, or maybe start studying in your upcoming semesters. Okay, so till now we have considered that if both of the engines are having the same amount of fuel and they are burning at the same efficiency. Okay, now try to understand that what is the combustion of the engine and what is happening inside the engine, and how both of the engines are trying to take the benefits of the engine design in terms of the engine combustion. Okay, so and why I chose basically this subject is one of the mysterious, as I said earlier. Nobody till now said confidently about this very subject, because nobody even figured out what is exactly happening inside the engine to the 100%. There is a myths, are there some rule? There's no any rules of thumb. It's similar kind of a thing will happen. They're just mere expectations of just mere guesses are there. This may happen inside the engine. The similar kind. Let's try to go through the basic parameter of the engine. Means what are the basic or what are the fundamental parameters of the combustion of any of the engines. Okay, so let's talk about the combustion. Okay, so this is the basically I taken this is the picture of the Bosch engine basically. So this is basically the diesel engine. Okay, and this is something like this combustion is happening in any of the engine. Regardless, this is the petrol engine or a diesel engine. Let's try to get into the combustion of any of the engine. So let's talk about the combustion. The factors affecting the optimal combustions. I'm going to talk about the optimal combustion. Optimal combustion, basically the combustion which is best at its own. Nothing can be expected beyond this. That is known as an optimal combustion. Optimal or best, as well as considering all of the parameters in a safer boundary. For example, you may have the best combustion, but at the same time you are we can say you are making lots of loads on an engine. Okay, but that is known as the optimal combustion. Optimal combustion is the best output from the engine by considering all of the engine design in a safe position. Your engine is not going to blow. Your ball is not going to get out of the engine. Everything is in a safe condition, but maximum out of the engine. That is known as optimal combustion. Okay, and let's try to define the parameters which are affecting the optimal combustion of any of the engine. First is the compression ratio that you all are aware of. Compression ratio means. Second is the air fuel ratio, means you know that in any of the engine the fuel goes in a mix. Okay, the mix as a mixture of air and fuel Okay, the amount quantity of fuel and air within the fuel of the mixture, it's known as the air fuel ratio basically, that you all are aware of, I guess. And the third thing which is affecting the combustion, optimal combustion in an engine, that is a turbulence. How much mixing or churning of the fuel, the molecules of air and fuel mixture is done with each other, so that the proper mixing can be done and the better output can be expected of the engine. And the last thing is the inlet temperature and pressure of the engine. So I'm going to unfold all these four parameters step by step in upcoming slides. So I'm going to show you up what is the effect of compression ratio. For example, if you have an engine of 10:1 compression ratio, so what will happen to the engine if you increase the compression ratio of the engine to 12:1? Is it even further to 14:1, 15:1 of a gasoline case? Okay, so we will figure it out what will happen and what we are required to do in that case in order to make the engine safer one. So in the same case of air and fuel ratio, I am going to discuss about what is the effect of air fuel ratio on an engine. For example, if I send a lean air fuel mixture. Lean means large amount of air but less amount of fuel inside the engine. How combustion will happen inside, whether it will be optimal or not, whether combustion will be happening in a proper way or not, we will figure it out. Okay, same in a case of turbulence. Okay, and the same in a case of temperature and the pressure of the inlet air. So let's start with the compression ratio. Let's unfold each and every component step by step. So guys, I'm going to discuss with you the combustion process of any of the engine. Okay, and in these very graph, on the x-axis basically the crank angle is there, and in the vertical axis we have a cylinder pressure. And I try to make a similar kind of the diagram that you are already seen somewhere, maybe in your books, maybe somewhere on our internet stuff. So that's why I try to make this all the information in your in a way so that you could recognize all the things at very ease. Okay, so when we start, let's try to understand what is happening inside the engine with the crank angle. When the angle of the crank suspends, what happens? What kind of activities happens along with the crank? Okay, so this stuff is basically your compression stroke, basically the compression stroke. And before reaching the top dead center, somewhere at a point, we have a spark. Okay, you might have studied in your IC engine that there you found that the spark is always started a few degrees prior to the top dead center, not at the top dead center. Now I'm going to show you why. What is the reason behind it? Okay, so some of the spark is we can say that given at some degrees prior to the top dead center, and again the gas is continue to compress in that way, and the point comes when first we can say that the flame starts, or we can say the first molecule of the gas get fire or get burned. Okay, and if I let it go further, it goes in that way. The rapid pressure rise happens over there, and the bigger blast happens at the top of this very peak that you can see over here. Okay, and if the piston goes down, this pressure goes down to this very point, and this is the point at which the lowest possible means very we can say the remained amount of the fuel burned till this very point. Okay, so this is the again the further part of the combustion. So I think it's not very difficult to understand. You are already aware of this very thing. Okay, so I'm going to add some extra points over there. So what is the important things are there in this very part? Okay, so first important part is this: the point at which you give the spark and the time at which it actually get burned. So this is there is actually time gap is there. When you give the spark inside the engine, it does not find or it does not catch the fire immediately. It takes some time. You can find it out over here. It is happening at -20 degree and it is happening at somewhere -5. Considerably, you can find it out there is a 15 degrees of gap is there. So that gap is very, very important for us from engine design point of view. Okay, so when we design any kind of a practical engine, if I talk about Bajaj engine, if I talk about the Pulsar engine, any kind of engine, so this considerable gap is required to be considered in a mind while designing the engine. Okay, so it is effect, and step by step I'm going to show you how it will be, how it will affect the engine design if you do not consider this gap. Okay, over there. And in your common language, in engineering language, this is known as ignition lag. Okay, ignition lag that you are all are maybe aware of. Okay, so this ignition lag is very, very important for us. Okay, so this is the point after when the first molecule gets fired, and this is the point at which up to 70% of the fuel is burned. In this very reason, up to 70% of the fuel is burned inside the engine. And this is the reason in which remaining 30% of the fuel is keep on burning at the slower pace, depending upon the time available and depending upon the chemistry of molecules present over there. Okay, so this is the basic combustion of happening inside the engine. And another one important thing over here is this thing. This point, this again, when we design the engine, this point is known as a peak cylinder pressure. Okay, this point is known as a peak cylinder pressure, and that peak cylinder pressure must happen at some degree to the piston after top dead center. Now, this is very like a challenging point, and this is very crucial point to understand. For example, we have a piston at its top dead center exactly, and at that moment, if we fire the air fuel mixture, then what happens? And at that moment, the crank is completely in align with the connecting rod is completely in align with the crankshaft. And at that time, if we push the piston down, it will break everything over. So that is why what we do is we try to rotate the crank up for some degree so that when you push the piston down, it will keep on rotating its rotatory moment over there. So that degree is very important. And that degree is over here, I just mentioned over here, is about 18 degrees. So this degree is basically may change according to the engine design. So for the Bajaj engine may be different, for the Jama R1 engine maybe it will be different. And it may be different for the continental area also. For example, the engine you finding in India and the engine you are finding in the US or UK market, they may have a different design according to the manufacturing as well as according to the fuel available at that subcontinent. Okay. And this point is known as the pitch point or known as the hammering point. Hammering point. So keep in mind, guys, as and when engine runs throughout its engine RPM, whether it's running at idling RPM, whether it's running at its top engine RPM, this point always should be happen over there. This point should not move in this direction, or neither in this direction nor in this direction. So whenever you have to design the engine, you have to design this whole curve. You have to design the timing of the spark in a such a way so that this thing, the top peak pressure, always should happen at the required or at the specified point by the manufacturer. Okay, so this is the combustion process basically, and these are the basic steps that are happening inside the engine. Okay, so now in a further aspect, I'm going to show you the effect of the compression ratio. Okay, so for example, you have an engine. For example, you have an engine of 10:1 compression ratio. For example, if you want to change that very engine to 12:1 compression ratio, then what will happen inside the engine? And what we are required to change considerably in the engine. Okay, so let's talk about. So for example, this is the base engine having 10:1 compression ratio. Over here, I am expecting that everybody know about compression ratio. Okay, so compression ratio basically means how much volume you are compressing during the. I'm not repeating that very point. Okay, so if I talk about this very slide, this is the base engine having 10:1 compression ratio. For example, you by any changes by mechanical changes or by any kind of a mechanical system change, you made that very engine up to 12:1 compression ratio. So what different kind of a peak will be generated in that very engine at the same RPM, and considering and assuming a same amount of the fuel is going in that very engine also. Okay, so in that very case, this peak will happen over there. Okay, so this is the 1:2 means this is the 10:1 compression ratio, and this will maybe the higher compression ratio, or we can say that the 12:1. You got my point? So this kind of a peak will be happen over there. So you can understand that you can find it over here. There's one glitch is over there. We haven't changed the timing of the spark. For example, in this very engine, we again fired the spark at the same time as we did in a previous case. What will happen? This time will be shortened by some time. In this very case, this time was a bit higher, but in this very case, this time is little bit shortened as compared to this one. So this is because when you compress the air and fuel mixture to a larger compression ratio, the molecules get closer to each other and it's more susceptible to get fired, or the time taken by the first molecule to get fired is very less as compared to the engine having the lesser compression ratio. Okay, that the first point that may be discussed in IC engine books, that is the effect of compression ratio on the engine. Okay, so this may happen, but the point is this is the thing that we don't want, because what is happening in this very case, this thing is getting shifted. Although we are getting a higher peak pressure as compared to this very case, okay, but this peak is getting shifted into this direction. And you know that this is undesirable. So what I need to do in this very case is, I need to shift this very point somewhere over here so that this point can also shift into this direction. In next part, I'm going to show you up in that. Okay. In that way. You got the point? I guess yeah. So what we did in this very case, if we are going to increase the compression ratio of the engine, we have to shift the timing at which the spark is required to be fired a little bit late, so that we could have this point similar to this very point, and we could have a peak higher than this, but in a line with that way, so that we could have a pressure at a specified point according to the engine design. I hope you understand at this very point. Okay, if anybody have any doubt, please give the point in a chat box. Okay, so further on, I am going to discuss the further one aspect. Okay, so this is the effect of compression ratio. Means if you are going to change the engine, the compression ratio of the engine, you are required to change the firing time, the spark timing of the engine also. Okay, so do not forget to change the timing if you are changing this compression ratio of the engine. Okay, so next point is I am going to discuss with you the effect of air and fuel mixture on an engine. For example, we have an engine, any of the engine, your regular pipe. Okay, first case, for example, let's try to understand that what I am going to show you up. I am going to show you up if you are running the engine at a lower engine RPM or at an idling engine RPM at a speed of 10 kilometer or 20 kilometer per hour. At that moment, whatever kind of air and fuel mixture getting inside engine is burning differently as compared to the air fuel mixture going inside the engine at higher engine RPM. I'm going to show you up how. So basically, air and fuel mixture can be of two types that you are aware of. That is a homogeneous and the heterogeneous. Homogeneous is completely mixed one, and the heterogeneous is in which the air and fuel mixture is completely not mixed with each other. The diesel engine is the best example of this very case. So over here, I just took one demonstrating video that will show you up how a heterogeneous engine, how a heterogeneous air and fuel mixture will burn in nature. Okay, and how it will be different from homogenized engine, homogenized air and fuel mixture. So that accordingly we could conclude what may happen when the air and fuel mixture is not properly mixed in an engine, when is properly mixed in an engine, and how it is going to perform in an engine. Okay, so the first point is the heterogeneous engine. Try to see this very video and pay attention in this. So guys, what happened in this very case, I'm going to let you know that what was there. Actually, we did a small experiment with the hydrogen. Okay, we'd taken a balloon completely filled with hydrogen, completely hydrogen, nothing else. Okay, what we did is, and you know that inside the balloon there is nothing other than the hydrogen. And you know that when we will burn this very balloon exactly, so there is not proper mixing with hydrogen and the oxygen is there. So that is why it will take some time to get fired, okay, and to get mixed with the oxygen present in the environment step by step. So that is why it is taking some time. So now in our next video, I'm going to show you up what is a homogenized mixture. In that very homogenized mixture, what we did is we taken a balloon of filled with the hydrogen as well as with the oxygen in a same proportion, in a stoichiometric ratio, or we can say that in a chemically correct ratio. Means whatever amount of oxygen is required to completely burn the oxygen. So you can find it out means how that balloon will burn in a case, and what is the difference between these two. Okay. So this is the case of a hydrogen with oxygen, and that is completely different from heterogeneous air and fuel mixture. And you can find out the difference between these two. Only hydrogen and a hydrogen and oxygen. So exactly, guys, this is happening inside the engine when your engine is completely homogenized and when your air fuel mixture is not homogenized, is heterogeneous basically. And you can check it out if the air and fuel mixture is heterogeneous, or we can say that as shown in a video, it will take little bit longer time to get fired or get we can say that completely burned. And if I talk about the homogenized mixture, it will take very less amount of time to get completely burned. And again, it will give you blast in a small time. you can find it out the difference, because we are an engineer, we can understand what is impulse. You are getting the same kind of a force, but what one force you are getting in a this very time or longer time, and another force you are getting in a smaller time, and which one is better, which is the impacting one? Yeah. So that is a homogenized one. So that is the thing which is required, that is expected from gasoline engine. So we are required to provide a homogenized air and fuel mixture inside the engine, so that we could find a better performance out of the engine. Okay, so let's try to and now in a further graph, I'm going to show you up means how the engine combustion will happen if you run the engine at a low at a different air and fuel mixture ratios, at a linear air fuel mixture ratio as well as rich air fuel mixture ratios, how your engine will do. Okay, so again in this very graph, there is on x-axis there is the crank angle, and on the y-axis it's the peak pressure of the cylinder. Okay, take the first case. For example, we have just started the vehicle. We just started the vehicle with the help of a key, and you're running that very vehicle at idling. At that moment, sorry, I cannot. No, I'm not going to take that very example. That is for something else. Another example, for example, we are running our vehicle at very lean air and fuel mixture. Lean air and fuel mixture means lots of air but lesser fuel. At that moment, what will happen? So something this will happen. Okay. So at this moment, air and fuel mixtures ratio is 18.1, means 18 units of air is there and only 1 unit of the fuel is there. Okay, so in this way, the combustion chamber will behave. The pressure inside the combustion chamber will behave. Okay, for example, if I increase the air and fuel ratio in a way so that, so guys, you are, am I not audible?
Yes, sir, you're audible.
Okay, I am audible. Okay, thank you. Okay, so guys, I was talking about effect of air and fuel ratio. Okay, and so the first graph that I shown you, that is according to the 18.1, means 18 units of air and 1 unit of fuel. Just a minute. Cursor cannot be seen, huh? Just a minute. Okay, I will try to include the cursor, the indications through my the discussion. Okay, if actually the cursor is not visible. Okay, so if I talk about this very air and fuel mixture graph, okay, the first thing that I showed you at very lower like a lean air fuel mixture. Okay, so if I talk about, for example, if I increase that air and fuel mixture to be little bit richer, means lesser amount of a fuel, a lesser amount of air, but with increased amount of fuel. So what will happen? This will happen. In this very case, we have a air fuel ratio is 16.1. Okay, 6 means air is less and fuel is little bit more, and you can find it out. The peak is little bit increased. Okay, so this is because larger amount of fuel is present over there. Technically, larger the fuel present over there, obviously larger the bigger blast will happen. Okay, larger the cylinder pressure will be happen. And the next thing, if I increase the in that way, you can find this thing will happen in this way. Okay, and in case of the gasoline engine, that is mistakenly written over there. That is not a 1.47. That is a 14.7. That's basically 14.7 that you all are aware of. That's a stoichiometric ratio or chemically correct ratio for the gasoline engine. Okay, and for the gasoline correct ratio, this will happen. And if, for example, if I increase the air and fuel mixture ratio, even if I make the air fuel mixture a bit more rich, then what will happen? So this will happen at the ratio of 12.1. Okay, so if I increase the ratio, if I make the air and fuel mixture a bit more rich, then what will happen? This will happen. I mean to say that there is a point that's a 12.1, 12 is to 1, sorry. That's 12 is to 1, up to which the combustion can be enhanced. But if you go for enrichment of the fuel beyond 12 is to 1, there is no significant effect will be happen on the cylinder pressure. So your engine technically should not be run further 12 is to 1. That should not be. Okay, that can be fired on even 10 is to 1 or even more if the engine is running in a idling conditions or in a cold conditions. Cold condition means when your engine is when you're riding your bike in a cold like in a December, in a month of December, when the bike is too cold to start, then when you require to use a choke. In a choke condition, you can go even richer up to 9 is to 1. Okay, but at that moment you cannot bet on the proper combustion of the engine. That just ensure yes, your engine will fire, but it will not use the air and fuel mixture completely. So if I go for the complete uses of the air and fuel mixture, I need to go for 14.7 is to 1. If I want we can say that higher combustion, or we can say that best power out of the engine, we are required to fire the engine on 12 is to 1. Okay, this is the thing I want to. So this is the effect of air and fuel ratio on engine. Okay, if you change the air fuel ratio, this will happen on the engine. Okay, so I hope you understood the point, and I'm going to the next point. So effect of turbulence. Okay, turbulence, being a mechanical engineer, we are very well aware of turbulences in a fluid. Increase if we design the intake manifold of the engine in such a way so that the air and fuel mixture should come inside in the engine by getting mingled within them. Okay, so that they could make a proper mixing with each other. Okay, and they could combust better. So air and fuel mixture in a proper way, we can say the performance of the engine is better. But let's try to understand how it is so. Okay, so basically let's try to understand that through a graph again. So this is the base graph. Okay, so for example, we are going to increase the turbulence. We are going to increase the turbulence, and one thing I can make you share that make you sure over there here how we can make a turbulence in engine. We can make a turbulence in air and fuel mixture by changing the design of intake manifold, by changing the design of intake valve, by changing the design of piston crown, by changing the design of air and fuel that's air filter, and changing the design of air filter conduit from which the air is being taken out. So these all the parameters with the help of which we can change the turbulence of any of the engine. Okay, so different engines have a different result. For example, if I take example of R15, so that is very well designed. The intake manifold of the R15 is better, is designed better. Okay, as compared to any of the 150 segment bike. So that is why the performance of R15, the throttling response of the R15 is better. Throttling response means as and when you give the response, it is give like a blip. So that is the quick response of the bike. Okay, so that is depends upon the intake manifold design. So for example, anyhow, if we increase the turbulence of the engine, what will happen? If we increase the turbulence of engine, molecules comes closer to each other or mixes properly with each other. So that leads to give you a higher peak cylinder pressure. But the point over here is, if we fire the same ratio, means air, we can say that same stroke in a same with the same spark timing, the peak of the cylinder will be shifted a little bit again toward the top dead center. So what we are required to do is, you know that we are required to put spark, means the spark timing a little bit later, so that we could get another peak which could have this, we can say that peak pressure, the same specified point at which the engine is designed to be. Okay, so this thing, the shifting of the spark timing is known as the ignition timings. Okay, and that are controlled with electronic units in a bike. You might have heard about TCI, transistorized controlled ignition system. So these are the we can say units which are basically helping us to change the spark timings according to the various parameters, okay, inside the engine. Okay, so this is the effect of the turbulence on the engine. So if turbulence of the engine increases, this will happen inside the engine. Okay, so next thing I am going to show you up the combustion with the engine speed. Okay, so what I'm going to show you up in this very case, what is happening inside the engine when you're going to start your vehicle from zero. When you're, for example, you just put the key in the bike and just given a key, and just give a start. For example, in the first moment, it didn't start, it just missed. So what will happen? This thing will happen in your case. So that is your motoring curve that you might have gone through in your IC engines. Okay, so this thing will happen when you are just gave the key, when you just gave the crank or gave the self, but engine did not start. So the compression will happen, but it did not get begins the point or get started. Okay, for example, if you just manage to start the engine, okay, by with the help of choke or something else, okay, just in, for example, now the engine is started and engine is running at the idling speed. Idling speed is basically the speed at which you are not drawing any of the power out of the engine. Engine is running on its own. For example, you're on a traffic. You do not put your engine off. You let your engine to be run on its own. You are not drawing any power out of the engine. That is idling speed. Okay. So if you are running the bike in a idling speed, so this kind of a pressure curve or pressure peak you will get. For example, if you increase the speed of the engine further on by putting your vehicle in a second gear or third gear, this thing will happen. And this thing will happen. And finally, this thing will happen if you're running your vehicle at very higher engine level. And one thing is common in all these peaks is this thing. You got the point what I mentioned over there? The line, the points at which each and every curve is going to be have a peak pressure, or we can say that blast. So that point should be at the same same point that is known as a specified point of the engine. Okay, so that you could get the better output of the engine. So this is like something it's happening inside the engine. These are basically the technical points which we are required to consider before designing any of the engine. Although I have just chosen a few points, only 3 or 4 points to discuss, to make this very discussion very healthy or knowledgeable and very understandable basically. But if I talk about practically, there's a n number of parameters which we are required to consider before designing any of the engine. Even you can say that if I change the valve diameter, the valve diameter, intake manifold's valve diameter, the engine performance will be different. There's lots of parameters are there which are required to be controlled simultaneously in order to get the desired output of the engine. Just for the sake of making, just for the sake of simplicity, I just chose a few points to discuss to this very lecture, as I think we have already 1 hour. Okay, so I'm going to, so I will wrap up all the things in a slides, in the further slides. Okay. Now in the next slide, I'm going to show you up what are the design benefits taken by the both engines. The both engines we started with, the KTM 390 and the RE350 engine. Okay. If I talk about the KTM 390 engine, the KTM 390 engine is basically having a higher compression ratio as compared to the, yes. Okay. But in the case of the RE350, it has the higher stroke length as compared to the higher compression, the KTM 390. Okay, so these both of the engines are not compromising in any of the points, but they are the best in their like a segment. They are the best in their segment. They are not. They are. If somebody asks me, sir, tell me which engine is best out of these both, I cannot say anything, because that depends upon, because both of the engines are for the 2 different categories, for different applications. Okay, from engineering point of view. So if I talk about, in order to enhance the engine performance further on, the KTM 390 basically use the TCI ignition system. So similarly, in the case of RE, we use the TCI ignition system. TCI, please check in case of RE, that may be the CDI, I guess. That's a CDI, the capacitor discharge ignition system is used in the case of the RE350. In case of KTM 390, there's a fuel injection system is used. The injectors are used to push the fuel. But in the case of 350, there is both kind of systems are available with the carburetor as well as the fuel injection system is there. But in a case of KTM 390, we have the liquid cooled engine. That's the liquid cooled cooling system. But in the case of RE350, we have only air cooled system. Okay, so that are the basic difference between these 2 engines, which are making both of these 2 engines best and in their segment. Okay, so this is the design aspects of the design benefits taken by both of the engines. Okay, and if I talk about the engine design targets, if I talk about the companies, how do they design, what kind of parameters they consider before designing the engine. Okay, first is the intake manifold design, intake maximum amount, so that the maximum amount of air and fuel mixture can be taken inside. Okay, so they design the the intake manifold in such a way so that maximum volumetric efficiency can be achieved. A larger amount of fuel can be induced. Second is the combustion chamber design, so that efficiently the combustion could happen. Third is ignite the air-fuel mixture at optimal order to have an impact. In order to have at optimal point means in this very point I'm talking about the same point, the specified point. The ignition should happen in a such a way so that the peak pressure should happen at a specified point on the crank. The fourth thing is the minimizing the heat loss by compacting the surface to volume ratio. Larger the surface to volume ratio, larger the area for the gases to escape into the environment. So they try to reduce the surface to volume ratio. Okay, so that just try to, you might have as we are engineers, we have studied this very through in a mathematics in 12th standard, calculating the maximum volume means a ratio of surface to the volume. So in a case of the spherical thing, having a least surface to volume ratio. Okay, so that's why we try to make the cylinder in a spherical range, in a case of spherical, the dome of the cylinder in a case of spherical, so that the lesser amount of heat could be escaped to the engine, from the engine. Okay, the next thing is the compact combustion chamber that helps in reducing the flame distance. That is very crucial to understand. Bigger the cylinder, the larger distance is required to travel by a flame, which is going to fire each and every molecule. Larger the distance, obviously you can understand lot many things can happen, like knocking can happen. Okay, so pre-ignitions, like this kind of things are very common to see in this range. So the next or last thing is the good squelching and exhaust of the exhaust gases. In engine design, basically these are the design aspects which we are required to look upon before designing the engine. Apart from the structural thing of the engine, means about the crankshaft, means a load on a crank. That's a structural part. That's the designing part, or conceptual. We can say the concept points of the engine design. Okay, that we are required to think about. So next, I am going to show you up small things on the effect of knocking and abnormal combustion. Okay, so guys, knocking is already aware to all of you. Knocking, what is knocking? So in some of the pics, I'm showing you up the piston, the blown head pistons. You can see that in a case of the piston, the outer top of the piston is gone because of the knocking. That's an abnormal combustion basically. And if we talk about in a case of spark plug, the fault spark plug and the tip of the spark plug, it's gone away because of the harsh combustion inside. And in the case of the valve, you can check it out what is the situation of the valve. And in the case of the cylinder head, you can check it out. In a cylinder head, one of the valve is missing because of the abnormal combustion. This can happen inside the engine. And if I talk about the abnormal combustion is basically uncontrolled combustion inside the engine. If we are not controlling the combustion inside the engine in a proper way, it is going to get out of your control and it may damage the engine. So this is all about the combustion and its basic aspects of engine design and parameters. And I hope everybody learned something out of it. And this might give you something, some different edge apart from your classroom studies. Because, but my aspect was really very to go in a way in which the subject is being taught to you. So I try to take the figures in a similar way that you could get the ease to understand the pictures. Okay, so that's all from my side. Thank you very much. And if anybody have any questions, please pop in the chat box. Okay.
Thank you for the session. So we have this forum open for question answers. Students, you can ask the questions coming near the screen, or you can use the chat box which is available. Velamar College, is there any question from your end? Just raise your hand if you have got any question. I'll unmute you. Okay. Yes, please go ahead. Please ask the question directly near the screen. Meanwhile, he prepares his question. Do we have any question coming in from KK Wag? Just raise your hand, KK Wag. Okay, I see a question coming in from the last benches of KK Wag. Is it true? So there is a question on your screen.
Yeah, I got the questions. Okay. So what is the effect of turbulence on fuel efficiency? Yeah. So please mute all of the students. I am getting some of the disturbance from one
Yes,
side.
I'll mute all. Yes, just give me a moment, please. Sorry to interrupt. Yes, Yash.
Yes. So anything else? If please, if you allow all the questions to be present on the screen, so I can answer all of the questions in single go, one by one. You can ask.
Okay, we've got two questions, one from KK Wag and one from Velamal College.
Okay. So any else? Anything else? Okay. So I'm going starting with the first question. Okay. What is the effect of turbulence on fuel efficiency? Simply, guys, if I talk about the fuel is required to used, and fuel is required to be converted from its one form of energy to the another form of energy. Okay, so if we could use the fuel in a proper manner, or we can say to the maximum efficiency, then obviously it is helping us in a fuel economy. But now the point is how the fuel economy, how the air and fuel mixture can be burned efficiently. And the turbulence is one of the method which can be used to increase the fuel economy. And in a turbulence, how it is happening basically. So in a case of turbulence, what happens in stream? If I talk about the air fuel mixture inside the which is coming inside the engine, that make a stream of air and fuel mixture, like any of the fluid that you might have seen passing through any of the conduit or a pipe. But over here in a fluid, we have two elements are there, two things are there. One is air and another is the fuel. And inherently, because of the design of the conduit, the air and fuel mixture cannot be mixed to the 100%. Cannot be. Okay. But can be enhanced with the help of some kind of mixers inside the tubes. Okay. We can design the size of the tube in such a way so that when the air and fuel mixture having two different elements, air and fuel, inside that, when these two things are mixed with each other, when the one-to-one molecule is present to get burned, then its fuel is that the efficiency of the burning of the fuel can be increased. And technically, in any of the engine, the maximum the homogenizes, we can say that efficiency reaches up to only 95%. Again, there is a 5% is there, which can be resolved with the help of other turbulence factors by increasing or by introducing something else with the help of which we can increase the mixability of air and fuel mixture with each other. So that is basically providing one-to-one air and fuel mixture which can burn. That is increasing the efficiency of the fuel with the help of a turbulence. Okay, so I guess who's ever asked this very question, and you might get the correct answer from my side. Okay, so I am coming to the next question, and that's while creating the turbulence, whether the manifold. Yes, the question was if you are not able to see the questions written on my screen, that's while creating the turbulence, whether the manifold intake affected by cavitations, and that is the question is yes. Obviously, if there is a irregularities is there in an intake manifold, is obviously that will affect. Yes, one thing I want to tell you that the effect of this thing may not be very, very prominent, which may be visible with any modern, we can say that equipments. But if I talk about its effect, yes, its effect is yes. But its effect, how much it's considerable, that is not a point of question here. If I talk about its effect, yes, it is effective. Okay. So if I talk about the next question, how can we increase the combustion efficiency of a combustion? Okay, very interesting questions, by the way. And if I talk about my whole presentation, it is basically based upon the same thing. Okay, and in this very presentation, I have discussed with you various parameters to which we can increase the peak pressure. Peak pressure of the engine, basically the efficiency of the engine. We are getting maximum out of the same amount, given quantity of the given amount of the fuel. Okay, and there is a compression ratio is the one of the point. We can increase the efficiency of the engine by compression ratio, by mixing the air fuel mixture in a proper way. And third is by increasing the air and in temperature and pressure of inlet air by some amount, not to the high. If we increase the air and fuel, the temperature and pressure of incoming air to very high, the volumetric efficiency of the engine will be reduced. Although your combustion efficiency will increase, but the volumetric efficiency will be reduced. Okay, so inlet air temperature and pressure, air and fuel mixture, and compression ratio. These are the three basic prominent parameters through which we can increase the combustion efficiency of the engine. Okay, and if I talk about the next question is from Karan Gupta. Yes. Now the question raised for the CRDI technology, that's a common rail diesel injection. And if I talk about the CRDI, that is basically the diesel technology. In a case of diesel, the diesel engine is basically different from the petrol engine. In a case of petrol engine, the air and fuel mixture is mixed, pre-mixed, we can say before to the combustion chamber of the engine. But in a case of diesel that you all are aware of, in a case of diesel engine, we have inside, we have the air inside the engine after compressing it up. After compressing it up during the compression stroke, we inject the fuel inside the diesel, inside the diesel engine. Okay, so if I talk about the CRD technology right over here, by the way, the question is a little bit confusing. It needs a bit more clarity. Means what Karan is looking from this very question. So if I talk about the CRDA, basically the CRDA is we can say that the electronic advancement on the diesel engine. So that in a mechanical diesel engine, the fuel is injected inside the engine with the help of a mechanical pump and the actuation system. But in case of the CRD technology, we have electronically controlled injections are there. With the help of the electronically controlled injections, we can control the amount of air and fuel, the amount of fuel to be injected, and the time at which the fuel is required to be injected inside the engine precisely. So that is a beauty of the CRDA engine. Okay, so this is all about from my side. If any question, please pop up on the chat box.
Okay, do we have any more questions coming in? Any question from DJ Sangvi? Or College of Engineering, Kerala? Okay, students from KK, just raise your hand if you do not have any more questions. Done. Okay, that is a final no from KK. Okay, so Yash, thank you very much for joining in, and the students can very well ask questions to Yash after the session too. If you can please share your email ID, Yash, the students will directly email you, or you can, the students can email the questions to VBind, and we in turn will post these questions to Prigma EduTech.
Yeah, sure, definitely. I'm over here. I'm writing my email ID. They're over here. Everybody can share any kind of doubts. Okay, and prominently, if anybody can like a Facebook page over there, we have a dedicated technical team over there, which is present over there to respond any of the questions, okay, from any of the students. Okay, so I'm writing over here the link for my Facebook page. So that's my Facebook page, okay, the company's Facebook page. That's the Prigma dot, maybe that's a Prigma Edutech or Prigma dot Edutech. Please do correct accordingly.
Okay, the students, please note down the Facebook address of Prigma Edutech. You can very well ask the questions, or we'll be posting this video on our Facebook page and on our social media pages. We will be tagging Prigma Edutech, and you can just directly ask questions directly to Yash. Okay, Yash, thank you very much once again. I hope
thank you very much.
Enjoyed the session.
Thank you very much, Vibind, and everybody present here. I hope everybody enjoyed the session. And
yes, so students, can we have a round of applause for Mr. Yash here?
Thank you very much. Okay.
Thank you. Students, this session was brought to you by Simply Learn. Now, Simply Learn is one website which is on a mission to educate and skill each and every student from the technology domain. So here is a short video by Simply Learn.
क्या लगता है आपको ऑफिस? ये शतरंज है और यहाँ सबकी एक ही इच्छा है, राजा रानी के केबिन तक पहुंचने की, पर सब किस्मत के भरोसे। ये आनंद है, simplylearn.com से सर्टिफिकेशन कर रहा है, बिग डेटा, डिजिटल मार्केटिंग, प्रोजेक्ट मैनेजमेंट, प्लानिंग की है अपने करियर को आगे बढ़ाने की। किस्मत पे मत छोड़ो, टेक चार्ज ऑफ योर करियर। simplylearn.com. Get certified, get ahead.
So the students can visit the website, that is simplylearn.com. There are a host of courses available right from technology as well as the business domain. You can visit all the courses here, and you can use the coupon code VBIND30, that is WEBIND 30, and you will get a flat 30% off on all the courses which are available on the website. Thank you very much for joining in. Thank you for being such a wonderful audience. Have a nice day.